Hey folks, I am coming to you from the inside of Capital Christian School, where I happen to be chaperoning Musical this year. Um, so you're going to look at the screen and think, oh my, what is Mr. Stefan doing? All right, so what I'm doing here is I have a couple things I just need to show you, and then we're going to do a couple example problems. The DF formula, degrees of freedom formula, let's change my color there. Let's go like that. My degrees of freedom formula is for a two-sample t-test. All right, a two-sample t-test. Here's how you would do it. And by do it, I mean you're never going to do this. So don't ever do this formula. But your calculator, when you do a two-sample t-test on your calculator, it gives you a degrees of freedom, which is usually a number that's a decimal place. This is why it's a decimal place, because it's this gigantic formula. Another time they might say df is equal to n1 minus 1 or n2 minus 2, whichever one is, 1. n2 minus 1 or n1 minus 1 or n2 minus 2. And they say use whichever one is smaller. That's a very, very, very conservative estimate that you're not going to usually use. Instead, you're going to use this DF gigantic formula, but it does it in your calculator. You do not have to memorize the formula. You never have to write the formula down. It's not on your formula card, so don't really honestly worry about it. But some people ask, like, where does it actually get that big giant DF from? Here's where it's from. Could I go through and show you why it is the way it is? No, I can't. I don't remember doing it as in undergrad. I've never actually derivated this out, so I've got no clue. Sorry. Then over here we've got two z-score formula for doing a two-sample. This first one is for a two-sample proportion test. Two-sample prop z-test. All right, it's a two-sample proportion z-test, and I know that because it's got the p-hats in there. All right, remember this thing over here, that's whatever your null hypothesis was. In many cases, it's going to be 0. Is it always 0? No, sometimes they say, hey, is this proportion more than 1% of the other one, more than 1% greater. So your null would be that one of the proportions plus 1% is equal to the other proportion. But in most cases, it's going to be a 0 number. All right. Remember down here also we've got this C for all these P's and Q's. That C stands for combined, right? And when we did the combined in an example, it's the total number of successes. So I've got two samples, so how many successes in the first sample plus how many successes in the second sample, divided by the two sample sizes added up. All right, and the reason why we use combined again is because we have to assume in the null hypothesis that P1 equals P2. If they are equal, then we assume that even though we do two independent random samples, remember we do two independent random samples, even though we do two of them, we're going to assume that both populations that we're drawing from are the same. So we're going to treat it as if it were just one gigantic sample, and that's for P combined for figuring out the standard deviation of the sampling distribution, which is what is in the denominator, standard deviation of the sampling distribution. All right, the second Z formula is for doing a two-sample Z-test. Very, very seldom are we going to do this, and the reason why is in a two-sample z-test, you have to know both of the sigmas. All right. Most of the time, we don't know one sigma from one population. How are we going to know both sigmas? But if we did, this is the formula that it would be. The difference is, then how does this transform into the t? It's the exact same thing, only we replace with S1 squared. All right, and then over here, we replace that with S squared for the second sample set. All right, where's those numbers actually come from? They come from the sample of the data. So if it says, hey, we did a random sample, we got a standard deviation and a mean, then you plug those numbers in there for standard deviation to square them because it comes from a sample. All right, a couple other formulas here. Let me clear out this layer. All right, confidence intervals. We have confidence interval for a proportion, so we're going to have a two-sample proportion, or it's actually going to be a two-prop, when we're doing our calculator, two-prop Z interval. We're going to do a two-prop interval. We can do a 2-prop interval as well. Or sorry, not 2-prop, 2. Okay, I'm messing things up. You gotta stop me. 2 sample. Remember, we can never have a 2-prop t interval. So then we're gonna have a 2 sample z interval. So up here we'll have p hat 1 minus p hat 2 plus or minus z, because that's our critical value, times p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. People say, hey, wait, shouldn't they be combined? And the answer is no, because we do not have a null hypothesis. I have no idea what p is from one sample versus another. That's why I do a confidence interval. I do a confidence interval to estimate where p really is. So if I don't know p, I can't put in a value for p, much less a p combined. 2 sample t interval, x bar 1 minus x bar 2, plus or minus t times s1 squared over n1 plus s squared 2 over n2. Your calculator will ask you if you're going to pool it, and we never pool. Never pool. I can show you how to pool, but I don't know why I would want to, since we will never do it. X bar 1 minus x bar 2, you know where this is going, plus or minus z times sigma 1 squared n1, sorry, sigma 1 squared plus sigma 2 squared, it's all under the square root, over n2. There's all my formulas. It's a lot of formulas, but they all follow the same basic function. Statistic plus or minus critical value times standard deviation of the statistic. All right. Remember though, and I've said this before and I'll say it again, this number here, all right, so like when you're doing a free response question, usually we're going to do the test statistic first, and then like part D is now quickly do a confidence interval and estimate where the mean is. That z or this t or this z are not the same as the test statistic. All right? This is determined by my confidence level. So if they say 99%, I have to look on my chart and I think it's 2.33 for a z. If I'm wrong, then I'm mistaken at this point. Why don't you check that on me? For the reflection response, check and see what the correct z-score is for a 99% confidence interval for z. Do the same thing here for t. If my df, let's say my df is 60. So look in there for a 99% confidence interval and indicate the corresponding critical values for z and t. Do that in the reflection response. Tell you what, I'm just going to leave this as it is, call this one video done. I'm going to do a couple examples in a follow-up video to this, so see you in class.